Idea continuous, the functional value equals the limit. We talked about how you could have endpoints from the left and the right. We talked about types of discontinuity. We had continuous functions, and luckily most of what we think about is polynomials, sine and cosine, exponentials, lines, logarithms, all of those are continuous. We talked about removable discontinuity, which was just like 1 point being removed. We talked about a jump discontinuity, and usually we think of that as like a piecewise function or something that we have a jump in. We talked about infinite discontinuity, which is vertical asymptote. We talked about oscillating discontinuity. That's pretty much like the one example. That's not one we really experience much anymore, but it's out there. And so we were at this question yesterday. Isn't this where we left off yesterday, I think? Yeah. So as we continue here, so first off, we have this function, x cubed minus 7x minus 6 over x squared minus 9. So first off, let's kind of go through these various things here. We want to say, what is the domain? Where is this function not defined? So what values can x not be? Looking in the bottom, we say x cannot be 3 and negative 3, right? Plus or minus 3. Okay. So those are going to be our places where we're going to say, well, we're probably going to have a discontinuity at those two places, right? Because it's undefined there, so something's happening. So let's see what those have. So first off, I want to look at this function and think about what happens here. So if I take that function, and let me, so we can see that function. Let's see what happens if we put 3 and negative 3 in. Now we know right away the bottom is going to be 0, right? So if you have a calculator or you want to grab a calculator, just put 3 in there, see what you get in the top. And put negative 3 in there, see what you get. So you're just trying to figure out the top. So just put 3 and negative 3 in the top to see what you get.
I got 0.
Did you do 3?
Yeah.
That's not good, because what's 0 over 0 mean? You got more work to do. What'd you get?
Negative 3 is negative 12.
Negative 12. Okay. So there's something different between those two, right? 1 0 over 0, 1 is negative 12. So what does that mean? If you get a number over 0, right? Think back to our limits. Like a number over 0, that would be what in terms of a limit? That's infinity, right? Now we don't know left and right and all that. We're not getting into that. But because we get a number over infinity or number over 0, that's telling us we are getting an infinite discontinuity because we're going to have a vertical asymptote. We're not getting into whether it goes to positive or negative infinity. We haven't got to that part yet, right? That would be, we could do our limits from approaching from the right and all that kind of stuff. But because we have a number over 0, we know at x equals negative 3, we have an infinite discontinuity. Now, because we have 0 over 0, that tells us we got more work. Now, what does that tell us? Well, we know the bottom is that, right? Well, you get 0. But because when you put 3 in the top, you get 0. If we think back to our algebra, that tells us x minus 3 must be a factor. Because when you put 3 in, you get 0 over 0. But what are we left with? how can we figure out what we're left with, what that top factors into? What are you thinking?
The division, whatever.
Division, we actually just did this today in pre-calc. What I'm going to do, remember synthetic division? I'm actually going to pull this out. 3, 3, 9, 2, 6, 0. So we end up getting this. So what does that tell us? So that tells us because this can be canceled or removed, what kind of discontinuity are we going to have at 3? If you go back and look at your list of the different types, because we can cancel this out, removable. So we are going to have at x equals 3, we can have removable. Okay. Now, let me go to the calculator to help us visualize what we got here. So this is x cubed minus 7x minus 6 divided by x squared minus 9. So right there we can see what happens at -3. We get a vertical asymptote, which is what we got because you got -12/0. So we have infinite. That matches up with the graph. 0/0 usually means we can cancel something, which means we have removable, which means we can't really see anything. But that's because if we hit trace, we can't actually get to 3, right? If I change it to zoom 4, now what do you notice at 3? There's a hole there because we have the removable discontinuity, right? So we can see the hole, okay? So, part C, can we redefine f of x at 3 to remove the discontinuity? So what does that mean? Well, this is removable discontinuity. Am I able to basically fill the hole so it's no longer has a hole? It's no longer discontinuous. So how do I do that? Well, we've done a lot of the work already. What we want to look at is what happens to the limit as x approaches 3 of, and I forget what it is. Is it minus 7x minus 9? Is that right?
-6.
I don't remember. Is it minus 6? Yeah. So we want to find what's this limit. That limit is going to tell us where that hole is. Now, luckily for us, when you plug in 3, you get 0/0. So we know we got to do more work. Luckily, we've already done that work. This is x minus 3, x plus 3, x minus 3, x squared plus 3x plus 2. So as we approach 3, that goes away. We get 6, 9, plus 9, plus 2, plus 20, which is 10/3. Which, let's see, if we look here, does that look to be 1, 2, about 3 1/3? Does that look pretty close to what our graph is? Yeah. So looking at the graph, you're not going to find 10/3 by looking at this graph. But once you found 10/3, you can use the graph to see that's pretty close, right? If we trace, how close can we get to 3? So you can see 2.9, we get 3.23. 3.1, we get 3.42. So at 3, about 3.3333. Makes sense. So it looks like we're pretty close, okay? So, can we redefine it? Yes, we can. And so they call this the extended function, and here's what we're going to do. We're going to say, let's redefine f of x to be this. It is x cubed minus 7x minus 6 over x squared minus 9 if x does not equal 3. If x equals 3, this is 10/3. Now, write that down and then we'll, figure out, what did we just do? So if you think about this, looking at the graph again, here is our graph. And we have our vertical asymptote. So this is our graph for every value other than 3. This is our graph. And then what is the value at 3? 10/3. So what does that do? Fills the hole, right? So now, is this continuous at 3? Because what's the definition of continuous? Don't think pencil, right? The definition of continuous is the limit equals the functional value. And in our original function, did we have a limit at 3? Yeah, we just found that. But did we have a functional value at 3? No. So that wasn't continuous. Now, the limit at 3, and the functional value at 3 are the same. So we filled the hole. So it is now continuous at 3. Okay. So all that we're just trying to understand some of that. I think is there something similar to this? Find the value of k that makes the function continuous. Well, what does that mean? So notice this is from the left and the right of 2, right? If it's continuous at 2, the definition says the functional value at 2 has to equal the limit at 2, right? That's the definition. And if it's from the right and the left, what has to be true for the limit to exist at 2 from the right and the left? The limits from the right and the left have to be the same. So basically what you're going to do here is you're going to have to plug 2 in for x and find k so that they're equal to the same thing. Okay. They give you some detail here and they're like, okay, the limit from the left and the right have to be equal. So basically what you do is you plug the 2 in and then you solve for k. Because it has to be the same on both sides. Okay, so that's what these problems are. They kind of go from the definition, right? It's not always 2, is it? No. Okay. Here's one like we just worked on, right? Find k so that this is continuous at 3. Figure out what's the limit of this at 3 by doing what we're doing, and then find k. Okay. All right. Let's keep going talking about some functions, okay? All right, a continuous function. Some more definitions. A function is continuous on an interval if and only if it is continuous at every number in the interval. I mentioned yesterday that eventually we'll get to the fundamental theorem of calculus, and looking at it back there, it says for every continuous function on the interval a to b. I'm reading it back there. So it's saying it's continuous on an interval. So what does that mean? It's continuous at every point or every number on the interval. What does it mean to be continuous at a point? That goes back to this definition. It's continuous at a number if the limit equals a function value. So a function's continuous on an interval if every point in that interval, the limit equals a function value. Okay. The other definition, a continuous function is continuous at every number in its domain. So let's look what that means. Let's look at an example. So we have the function 1 over x minus 1. Is that function continuous on the interval from 2 to 3? So continuous on the interval means it's continuous at every point on the interval. So really what you want to think about is where is that not going to be continuous? 1, right? You got a 1 on the bottom. You're going to have a number over 1. That means it's going to be a number over 1. That means you got vertical asymptotes. We got infinite discontinuity at 1. All that kind of stuff. So is it continuous on 2 to 3? Yes. Is it continuous on 1 to 3, open interval?
No.
Why? Why do you say no?
Because you can't have 1 on the bottom.
Correct. Does that include 1 with the parenthesis?
No idea.
Right? If you include 1, it has a bracket. The parenthesis means 1's not included, right? So that is a yes. If it was this, that would be no, because that includes 1. What about the closed interval from 0 to 2? Does it include 1? So is it continuous?
No.
No. So if it has 1 in it, if it includes 1, it's no. Okay? So that's what it means to be continuous on an interval. So, is f of x a continuous function?
No.
Yes. Why? What's the definition of a continuous function? Read the definition for me of a continuous function.
A function,
A continuous function, not continuous on an interval, but what a continuous function is.
a continuous function is continuous at every number of its domain.
Okay, read the last couple words.
Is continuous at every number of its domain.
Okay, read that again.
Is continuous at every number of its domain.
It's continuous at every number of its domain. So, what is the domain of this function?
1.
X cannot be 1. So, is this continuous at every number in its domain? Where's the one place this is not continuous?
1.
But is 1 in the domain?
No.
No. So it's that idea. Continuous on an interval just means all the numbers in the interval. And if you're not continuous at all the numbers in the interval because the bad number, so to speak, is in there, then it's no. However, a continuous function just means where this function is defined, is it continuous? The answer is yes. So, our informal idea of lifting our pencil is kind of gets messed up here because you say, well, this doesn't have a vertical asymptote. It does, at 1. But is it defined at 1? No. So we're okay for a continuous function. Different from continuous on an interval. That's the difference between the two, okay? Now, if you have something like this, is that a continuous function? Is it continuous at every number in its domain? Is 2 in the domain? Can you find f of 2? Yes. So is that a continuous function?
Yes.
Is it continuous at every number in its domain? No, because it's not continuous at 2 that's in its domain. It's defined at 2. Now, just trying to get us to understand what this means. Is that a continuous function? Is it continuous at every number in its domain? Is it defined at f of 2? Can you find f of 2? No, it's undefined. There's no solution, does not exist. So since it doesn't exist at 2, 2 is not in the domain. So is it continuous at all the points in the domain?
Yes.
Yes, so that's a continuous function. Is it continuous on the interval from 1 to 3? No, because in case 2, that's where the break is. So that's the difference between these two definitions. This one is all about its domain. So if it's not in the domain, you don't have to worry about it. This is on an interval. And so if one of those bad numbers is in the interval, it's no. Does that make sense? So they're both used in different cases. A lot of times theorems will say on the interval. Okay. Now, so if we look at all these functions, polynomials, rationals, absolute values, trig, radicals, log, exponential, inverse trig, these are all continuous functions. That means they are continuous at every number in their domain. Now, is it possible to get a vertical asymptote? Yes, but that's not in the domain. So they're not continuous. Understand, right, as we just talked about, they're not continuous on every interval is different than continuous on its domain. Okay? All right. This, just so you know, we're not going to have to do much with this. If you take any composition, combine functions, add functions, subtract functions, multiply functions, divide functions, take f of g of x and you combine them in any way, if the function you started with are both continuous, when you combine them together, your new function is also continuous. So if we just said all those functions that we know, polynomials and trig and exponentials and logs and rational, all those are continuous. Any way we can combine them, we're going to get a continuous function also. Okay. Once again, continuous at a point, not necessarily continuous everywhere. Okay. All right. Let's look at the intermediate value theorem. So intermediate value theorem has a name, but I'm not going to necessarily, this is not one you're going to have to remember. An intermediate value theorem is an interesting theorem. It says, let f be continuous on a closed interval from a to b. So there's we're given it's a closed interval from a to b and it's continuous. That means between a and b, it's continuous. So our definition of continuous means between a and b, the limit equals a function of all those points. Here's another way to think about it. When you say it's continuous from a to b, in that interval, it's a nice, well-behaved, just a really good function. There's nothing crazy going on. You don't have asymptotes, you don't have holes, you don't have jumps, you don't have breaks. If it's continuous on the interval, you know we're dealing with a function that doesn't have anything crazy happening, right? There's no piecewise something or doing, just nice. This is a really good function, well behaved. Okay, that's what it means. So that's like saying, okay, hey, this is, you can draw it without lifting your pencil. There's nothing weird going on that interval. Okay, so if that's true, let n be any number between f of a and f of b, where they are not equal. There exists a c such that f of c is equal to n. What does that mean? So let's look at it. This is one of the first ones we look at that are known as an existence theorem. It doesn't tell you the answer, it just says there exists an answer, but you don't know what it is. So let's draw a picture. So this says, from some interval from a to b, we have f of a f of b. Okay? And it doesn't have to be like that. You know, f of a could be up here and f of b could be down there. It doesn't matter, right? They're just some points. It just says they can't be equal. This says we know this is continuous, which means if I start my pencil here, what do I have to be able to do to get to b? I got to be able to draw it without lifting my pencil. Nothing crazy is going on. I don't have an asymptote. I don't have a jump. I don't have a hole. Nothing crazy is going on because it's continuous all the way from A to B. This theorem says if there was an n between f of A and f of B, right? There has to be some number c where it equals that value. Because like we said, if I start here and I go to B, what can I not do with my pencil? Lift it. So it's somewhere there has to be a point C where f of c equals n. Now, we don't know what this looks like. This could go something crazy like that. So, there may actually be lots of C's. Does it tell us how many C's there are? No, it just says there exists a C. There may be more, but there has to be one. Because we know f of A does not equal f of B. So even if this is just a straight line, and there's only one C, there has to be a C that equals that. Okay? Could be more, but there's got to be at least one. That's like the idea of it's known as a existence theorem. It tells you there is a solution, doesn't tell you how many, it also doesn't want to tell you how to find it. But you know there is one. Okay? How do we use this? You have used this before. You didn't even know you used this. So let's look at this. Show x cubed minus x plus 2 equals 0 on negative 2 to 0. So, first up, intermediate value theorem. Is this continuous on that interval?
Yes.
Why? You're right, but why?
Because it has to be.
What's that?
It has to be.
To use intermediate value theorem, you're right. To use intermediate value theorem, it has to be. But what type of function is this? X cubed, lost it. X cubed minus x plus 2. Isn't that a polynomial? And then look at the top of your paper. What are continuous functions? Polynomial. Polynomials are defined, so everywhere this is defined, it's continuous. So we know it's a continuous function. So we can use the intermediate value theorem. Now, we're on negative 2 and 0. So if I take this function right here and I put negative 2 in, what will I get? 8, negative 8 plus 4 plus 2, so it should be plus 2. So this is 2, 4, negative 8. I get negative 4. Now, if I put 0 in, I get 2. So think about what this is saying. We don't even know what the graph looks like. This is saying at negative 2, it is at negative 4. And at 0, it's at a positive 2. This is continuous. So what does that mean if I start at this point? And I got to go to the other point, and I can't lift my pencil. How do we know this has a root somewhere in between? If I start here, what's it going to have to do? It's got to cross somewhere, right? We don't know where. We don't know what the answer is. Now, it may do this and have one answer. I mean, it may do this, have 3 answers. But if it's, do we know there has to be a 0 or a root between negative 4 and 2? Yes. So, show it has a root. There's got to be a 0 between those two. That's the intermediate value theorem, right? This is how your calculator finds zeros. If you ever do something on your calculator, and let me put in something simple, like this, and you want to find a 0, and you do it wrong, and you, let's say, go between those two, obviously there's no 0 there, right? The calculator tells you no sign change, because the calculator knows if you're looking for a 0, your 2 points that you pick have to have what? Got to have a sign change. One has to be positive, one has to be negative. In order to find a 0 between, you need a sign change. And so the calculator here is saying, hey, the 2 signs you picked, there's no sign change. I can't find a 0 when there's no sign change. Calculator is kind of giving you that error, which is related to the intermediate value theorem. Okay. If we look at the homework, Delta Math, you're going to kind of go through question. Function is continuous on negative 9 to 9. Below shows a portion of the graph from the interval from negative 5 to 0 is hidden from view. Given that f of negative 5 is negative 3 and f of 0 is 5, what conclusions can be drawn based on the intermediate value theorem? What's got to happen in there? And then if we scroll down, since f of x is continuous on its domain, can it be applied or not applied? Applied. And then once you do that, it's going to go down here and more, and it's going to ask you some more things to kind of answer that question. Let me show you what you'll fill in. You can apply, and then it's going to ask you to say, okay, between there and there, there's a 0, and you're kind of stepping through. Just getting you to understand what the intermediate value theorem means. Okay? All right. So that is 2.5, continuity. Big thing here is a lot of definitions. Okay? Intermediate value theorem, we'll use it. You do not have to have it memorized. The big thing here is remember this. What does it mean to be continuous? The limit equals the functional value at a point. Right? Once again, informal, you not lift your pencil, but when you're talking about a specific point, right, at a point, the limit equals a functional value. That's the key. Okay? All right.